So I guess we are back to Husqvarna special. Okay, let's get started because we are kind of running out of time as well. And I have plenty of stuff to talk about. So this first lecture will be more or less just a broad introduction to the data mining, what this is about, and kind of a brief overview of the basic concepts that we will go through later in the rest of the course. So just to give you an overview of the contents that we are planning. So this first lecture is about the introduction, then we will talk about decision trees, algorithms, we will talk about neural networks and support vector machines, we will talk about interestingness and association rules, visualization, data knowledge representation, and then one final lecture, anomaly detection and unsupervised learning. Because most of what we will be talking about is about supervised learning, but we want to touch some other concepts as well.
Excuse me, one initial question. Will these slides be available for us later on?
Yes, I will make them available.
So we have an interactive tool that you will also get access to eventually, and there you can find the slides, recordings, and also assignments and things like that.
Nice.
So we are just building all of those things, so it will probably take some time before everything is in place, but I will make sure that you can get access to the slides and the video as soon as possible.
Perfect.
And of course, anytime if you have questions about what I'm saying and so on, just feel free to interrupt and ask them. So just to give a brief overview of the data mining, what this is about, and there are of course a lot of different definitions, but it's basically about ways to discover patterns in the data. So you want to find different ways of finding useful patterns in the data. And of course, the definition of useful is quite broad and a little bit fuzzy. It's not clear what it means. So people have tried to make it a little bit more concrete by saying, well, they should be non-trivial, implicit, unexpected, previously unknown, and so on. So on one hand, the idea behind data mining is very much centered on the person who is going to learn something. So it's quite subjective area, and it's a little bit difficult to formalize all of the aspects of it. But there is, of course, quite a number of concrete tasks and concrete evaluation measures and so on. And we will go through a number of those, some of those today, some later in the course. And if we think about why data mining is so popular right now, this goes back to this old necessity is the mother of invention. And people have been saying that we are drowning in data, but starving for knowledge. And the idea is basically that we are, as human race, we are creating a lot more data than we have ever before in our history. But to actually get something useful out of this data is becoming harder and harder. So we need automatic tools to help us with that. And in that context, one way of looking at data mining is that it's just one of the many buzzwords. And if you think about different words that mean more or less the same thing, sometimes with different contexts, sometimes subsets of it. If you think of things like knowledge discovery, data analytics, business intelligence, decision support, machine learning, all of those things, different people use in different meanings, but they have at least a very big overlap with the data mining. On the other hand, if you think of the somewhat related fields, which are actually quite different, those would be things like search, query processing, or deductive expert systems. They all focus on knowledge as well, but they don't focus on this discovery of knowledge. So in that sense, those are not equivalent to data mining. So to continue on this idea of what is the reason behind data mining becoming so popular right now, people talk about this data gap in many different settings. And there are different ways of looking at this gap. So you can talk about for example, comparing the easy to use versus difficult to use data. So if you compare relational data to unstructured data, All of those graphs kind of show you how the data, the amount of available data grows over time. But the important thing is it's not only about the amount of data that changes, it's also the type of data that we are working with that changes. So, for example, we are getting a lot more unstructured data right now, a lot more text data, a lot more images data, and taking advantage of that is much harder than taking advantage of, for example, relational data. Another kind of...
Just a question, what is meant by unstructured versus relational data?
So relational data is data in which you have each let's say number has assigned meaning. So you would have, for example, a table, and there you would have speed, power, fuel consumption, and so on. So you know what each of the numbers means, and they are in a nice, easy to understand way, in a sense. Unstructured data would be something like images or free text, websites, and so on, where for any given symbol, its meaning is not obvious because it depends on other things around it, in a sense. There are other ways of looking at it. So there is a time to make decisions shortens while the amount of data that you need to take into account becomes bigger. The relation between relevant and irrelevant data is changing. If you look back, let's say 100 years, you would only write down things which are important. Today, you write down everything. So there is a lot more irrelevant data which is still stored and has to be somehow sifted out. So there is a lot of different ways in which you can look at it, but in general, there are two major factors for data mining to become so important, and that's the amount of data and the type of data that we need to handle. So if we think about some examples of whether something is data mining or not, if you think of looking up phone number in phone directory, is this a data mining or is it not? What do you think? Any guesses?
It's not data mining because it's trivial.
Yeah, exactly. That's not data mining. If you want to find out that certain names are more prevalent at certain US locations, so for example, O'Brien is more popular in Boston area, is that data mining or not?
That would be data mining.
Yeah, so that could be data mining. Now, if you frame this question as finding out which names are most popular in Boston, that's not data mining anymore, right? So if you know what you are looking for, it's not really data mining. But if you say, well, I want to find certain relations and you don't know, you want to automatically discover that there is difference in popularity, that it becomes data mining. How about querying a web for information about Amazon? Is that data mining?
You're searching for a specific name and topic in a structured environment, aren't you? So it would be no.
Yeah, so if we are just looking for a word Amazon, then not really. How about if we want to find the documents or separate the documents between Amazon rainforest and Amazon.com? Would that make it data mining?
I would say yes.
Yeah, exactly. So again, if the problem was simpler in a sense of you would want to find the occurrences of both word Amazon and rainforest, then it wouldn't be data mining. But if you want to figure out if a document is about Amazon rainforest, it's a much more complex task than just looking for the word rainforest. So if you really want to do it well, you need to do some form of data mining. So that's kind of the basic idea. And if you try to formalize it a little bit more, basically data mining is an algorithmic process. So you want to something that's possible to automate. you want to take data as input and you want to get some kind of pattern as output. And now the interesting question is what kind of patterns we are looking for, because there is a lot of different potential outputs from the data mining process. So we could be looking for things like descriptions or abstractions of data. So we want to summarize a document. That would be data mining. You could look for classification or association rules, for rules that tell you that certain things happen together. You can look for clusters or outliers or deviations in the data. You can look for different kind of sequential patterns like causality or to do abductive reasoning. You can look for regression, or you can try to do change point detection. All of those things, those are different kinds of patterns that you could be interested in. And in general, yes?
Question, what is abductive reasoning?
So abductive reasoning is reasoning about possible causes. So this is what you would do, for example, in diagnostics, when you say that, well, my engine doesn't work, what could be the possible causes for it? And then
okay, understood.
Figure it out. Mm-hmm. So for all of those different patterns that you can be interested in, you would need to design different methods to find those. So what is interesting is that from the same kind of data, you can potentially find different kinds of patterns. And I think that that's a very useful property. But the key concept in all of this is about discovery. This is all about finding something new. But what is important is also that the data mining, that there is kind of no wisdom in it. So data mining algorithms can discover new patterns, but they will not be able to apply them in any way. So, for example, they can find the relation between buying diapers and beer. And I don't know if you are familiar with this, but that was one of the kind of high-profile first success stories behind data mining. When people started looking at sales data in a supermarket, they basically noticed that, especially Friday night, there was surprisingly high correlation between buying diapers and beer. And turns out that young fathers who are sent to buy diapers, they just also have to buy beer to survive this traumatic experience. And that was a very, very interesting fact, because that really was one of the first cases of finding something new. It makes sense if you start thinking about it, but it's really something that nobody knew about. So you can use data mining to find such relations, but what's the next step? What you do once you have figured it out, that's a different question. Because as a store manager, you could be interested in putting those two together so that, first of all, you reinforce this tendency. So actually, people buy beer together with those diapers. And also you make your customers happy because they don't have to walk too far. Or you could decide that it's actually better to put them far away so that people have to walk throughout the whole store and maybe they will buy something else on the way. So to figure out between those two things, that you cannot do just using data mining. Here, you either need to add some more data about kind of the psychology of buyers, or you need to try to do different experiments and so on. So it's important to understand that there is some limits to what you can do with data mining. And in general, data mining will tell you about things that happened, but it will not tell you about possible things that could happen in the future if you change something compared to how the past looked like. So you can use data mining to kind of help to make plans, but data mining will not make those plans for you. And if you think about those kind of early successes, so the things that happened somewhere in, let's say, 50s or 60s last year, there have been a number of things that actually became so popular that now almost all of the industries is based on it. So, for example, bank loan is not done by people anymore pretty much anywhere in the world. It's all about machine learning and data mining. And this has evolved into other things. So insurance is now being done automatically. Different kinds of loyalty programs are managed automatically. All of those things are pretty much pure machine learning data mining. Another very kind of popular or high-profile success story was about travel behavior patterns. So when the airlines started changing the prices for their tickets based on different factors, that was based on data mining, and that has changed the industry quite a bit. And now it's not only the airplanes, now it's hotels who are doing it, and so on. So there is a lot of in a lot of industries in which the goal is to discover people behavior, you use data mining. The diapers and beer example started with supermarkets, but those kinds of approaches have also become quite popular in many other areas. So you use similar techniques today to do website planning, to do genome analysis, drug design. All of those things are based on somewhat similar association rules and so on. And you also started doing quite a bit of data mining in actual science. So when you look at astronomy or physics, a lot of the data that we collect today in those areas, it's too much to really be analyzed by hand. So you need to be using data mining to do those kinds of things. So there is quite a bit of work that went into this, and quite a few industries that have been changed by those kinds of things. If we look at maybe more recent success stories, so of course marketing is one of the areas where people are putting a lot of data mining. So figuring out how much to spend on marketing, what channels to use, and so on. And today you can basically start doing it on a very fine-grained level, so something like zip code level. So you can say that at different parts of a city, you can do marketing in different ways based on the type of population that tends to live there. If you want to model credit risk, that's something that, again, started maybe in the 50s, but today people have noticed that you actually can do it based not only on financial data. Today, people started using mobile networks, telecom industry started looking into this, and turns out that if you look at the the cell phone use behaviors, that's a very good predictor for whether somebody will pay back their debt or not. Kind of interesting. In a different industry, if you look at the Coca-Cola orange juice, turns out they are doing a lot of data mining because you cannot get the same types of oranges everywhere around the world. They have identified like 600 different types of oranges, and they use data mining in order to make sure that regardless of what type of orange you start with, you will always end up with exactly the same orange juice. That sounds kind of interesting. And there is a lot of work on the personalized shopping. So there are some stores which put RFID tags on clothes, and they will actually display video descriptions and some complementary offerings based on the clothes you try on. So you go to a store, you try on a number of clothes, and they will build a profile based on this and give you suggestions for what else you might want to buy and so on. So those kinds of approaches have started to really enter all the different areas of our lives. So if we kind of move away a little bit from marketing maybe and start talking more about the science, if we look at scientific definitions of data mining, there is a couple of them. You can look at non-trivial extraction of implicit, previously unknown, potentially useful information from data. That's one. Automated extraction of patterns representing knowledge. Discovering patterns in the data, automatic or semi-automatic. Patterns must be meaningful. finding hidden information in a database. So there is a lot of different ways in which you can try to phrase it, but again, it's all about finding something which is in the data, but it's hidden. It's not obvious. So obvious patterns are not data mining. If it's not in the data, then of course you cannot find it. So it has to be something that's hidden. And if you think about how this can actually be done, there are different ways of kind of formalizing the process of data mining, but it basically always starts with some kind of data sources. So you need to identify what type of data you are interested in and what type of data you want to be working with, what data you have available, and so on. Once you have your data sources, you want to do some kind of exploration. So you want to look at this data, try to understand it, try to see if it really is the type of data you wanted, if there are some errors in the data, something is missing, and so on. Just want to get kind of an overview of the data. Once you have done this, you do the modeling. So you want to create some kind of model or description of this data that you will be able to use later. And that can be, for example, a classification model or a prediction model. And I will talk more about this particular later on. And once you have built this model and you evaluated it and you are happy with the performance, then you want to deploy it. So you basically want to figure out how are you going to be making decisions based on the output of this model. So if the model will be predicting whether a customer buys something or not, how will you use this model to guide your marketing strategy or something else? This is the kind of general idea. And if you think about the kind of difference or what is new about data mining, if you think about reporting and analysis, that's very much about what has happened in the past. So you look at the past data and you want to visualize or explain this past data. And the data mining, the whole idea behind it is to try to answer questions like, why did it happen? So what kind of patterns you can see in the past that you can use then to predict the future. And that's partially why this data mining is always a kind of semi-automatic process, why you need to have a human in the loop, because we don't really have computer systems that would be capable of doing it on its own. And one way of looking at it is that you want data mining to move higher in this kind of knowledge pyramid. So if you look at this information hierarchy, at the very bottom, you have the data. So this is could be, for example, sensor information or history of sales or something like this. And on one level higher, you can transform this data into information. So information is data which is organized in some kind of useful way. Whatever this isn't, historically that would be done by people, but now the idea is that you would want to make those transformations at least semi-automatically. And then as a next step from information, you want to be building knowledge. So knowledge is the information which has been understood and integrated. So once you have combined several sources of information and you understand them, then you have gained some kind of knowledge. And the final step here is wisdom, which is distilled knowledge that then you can use to make decisions. So to know something is one thing, but then the next step is to actually be able to use this knowledge to make better decisions. So this kind of knowledge pyramid, that predates data mining. That's about how people do their reasoning. But then the data mining strives to reproduce this, at least partially in an automatic way. So if we look at the data mining process, how this actually should happen, we want to get from the data to knowledge. So as we talked about, that there is several different steps that you need to do. So you usually start with the data cleaning, because it turns out that when you collect data, there is usually quite a few problems with it. So you cannot just directly use this data. You need to clean it, you need to remove erroneous values, you need to do something about missing values and so on. Then you usually need to do data integration, because it turns out that all the data you need is not in one place. You need to combine several different sources. Then you need to do data selection, because you need to focus on a particular task. You have a particular goal, so you want to throw away the data which is not relevant for what you're trying to do. Then you do the modeling step, you evaluate your models, and if it works the way you want, then you can say that you have extracted some amount of knowledge. So those first steps you would usually do in a database. Then you would create some kind of data warehouse. Then you would pick a smaller part of this warehouse which is relevant for your particular task, and then you discover the patterns. And the tricky thing, of course, is that once you do this, it usually turns out that the results you are getting are not as good as you want to. So you need to kind of go back and fix the mistakes that you have done in different kind of stages. So this is a very broad overview of the data mining process. And we try to go a little bit deeper into how you would want to do it. The first very important step in data mining is to actually understand the application domain. So this is one of the biggest challenges that data mining experts have, is that it's not really enough to become an expert in the data mining itself. When you apply data mining to a particular area, you need to at least a little bit understand that area, because otherwise you will not be able to determine if the patterns you are discovering are actually useful or not. So you need to have a somewhat clear idea of what your application is about and what kind of task you actually want to solve. Once you have this idea, you want to create a data set which is relevant for this particular task. So you want to figure out what kind of data you need, what kind of data is available, how to organize it so that it's possible to work with it. Then you do the data cleaning and pre-processing. And one of the challenges is that this step is a very boring one, because it doesn't sound like you're actually achieving much. But it's also one which takes a lot of time, because there is a lot of different ways in which the data can be problematic. When the bad quality of the data is usually one of the biggest challenges, and dealing with that takes a lot of time. So this is something that's important to understand, that there is usually a lot of effort that goes into those kinds of challenges.
Can you give an example of what cleaning means in this sense?
So in most cases, it depends very much on what kind of data you are working with, but it's all about removing impossible data. So removing values which are impossible, removing sequences which are impossible. Mm-hmm. And this comes back pretty much from all of the time we are collecting data. We are never collecting it in a perfect way. And especially since data mining is about using large data sets, it means that... So
let's say that you log the data from a car, for example. If you have a clogged distance sensor, for example, that can be a case where you have to remove some of those values.
Yes, exactly. So broken sensors, communication errors, all of those things lead to data which doesn't really correspond to reality. And the problem is that such data can be very problematic for analysis, because it will skew a lot of the distributions in different ways. And it's generally not easy to figure out when the data is good and when the data is bad. So that's why it takes a lot of time. And the obvious cases, like if you have, let's say you are working with vehicles and you have vehicle speed of 999 kilometers, that's quite easy to remove. So obviously, that's bad value, doesn't make any sense. But there are many cases when this is not so obvious, and that's what takes so much time. Then the next step is you want to select the actual task that you want to do. So you want to decide if you want to do classification or regression or association rules and so on. Because usually for any kind of business goal that you might have, there are many different approaches that you can try to solve it, or many different types of insights that you could try to investigate. So you need to pick one and decide what you want to actually do. Once you do this, then you would pick a particular algorithm, and in most cases this will be some form of machine learning, and you will apply it to the data that you have prepared. And if you talk to different people have different ideas about the relation between machine learning and data mining and so on. Not everybody will agree with my view on it, but in the way I like to describe it is that the machine learning is the part where you have your data set, you know what you want to do, and then you apply a particular algorithm. Could be random forest, could be deep learning, could be support vector machine, could be clustering, any of those algorithms, and you get some kind of result. So this is one step in the whole data mining process. Once you apply the machine learning, this will give you some kind of patterns. Again, it could be classifier or clusters or anything else. Then the next step is to evaluate those results. So you want to figure out if the result you have gotten is good enough, if this actually achieves your goals. And then once you are happy with the result, then you can actually start using the discovered knowledge. So that's also an important step which a lot of people kind of forget about, is that the data mining itself, that doesn't really solve any problems. Data mining is about getting new knowledge, but then you need to think about how are you going to apply this new knowledge to actually get something better. So I have been...
question.
Mm-hmm.
At what part do you, I mean, if you have a large data set with different kind of scenarios, and
Mm-hmm.
some are scenarios that doesn't happen that often, and more are common.
Mm-hmm.
Where do you do the, you want your data mining process or machine learning, you want it to be learned evenly, so it doesn't focus on like one scenario because it's mostly represented in the data.
Mm-hmm.
At what stage do you do this kind of proportion, dividing up these proportions, and how do you, what is like what are the proportions basically? I mean, how do you weigh once? Sorry, yeah. I think you got my point.
Mm-hmm. Yeah, I get it. So that's a very interesting question, and unfortunately there is no simple answer to it. Depending on what you want to do and kind of how deeply you want to go into it and how difficult this particular problem is, you might try to do it in different steps. So you could try to handle this in the data cleaning step. You could, for example, either split your data into several problems, or you could do some kind of balancing techniques and so on. So you could basically try to say that the fact that there are different scenarios and some of those are very uncommon, that's in a sense imperfection in the data, and you would want to try to fix this imperfection in different ways before you go further in the data mining task. You could try to address this in the selecting of data mining task step, where you would actually kind of explicitly target different scenarios separately. You could try to handle this with machine learning algorithms, because there are some algorithms which are better in such scenarios than others. So you could say that you don't worry about this, but you will need to pick an algorithm which is robust against such problems. So there is a number of different ways of handling it, and it's neither of those is generally the best. So Either you would need to try a couple and see which works, or you kind of need to. The problem is that data mining is still, despite the fact that we are trying to teach it, it's still a lot of more art than science. So you need to have quite a bit of experience and so on.
Yeah. I would say a typical case, instead for an automotive area, is like if you have, let's say, situations which are dangerous, basically hazardous, either for the person or the equipment or whatever. It's hard to get those data points, but they are very relevant to get the knowledge or like the outcome that you would like.
Yes.
So, yeah.
So in this particular case, the bad news is that nobody has yet figured out how to do it. All the companies who are trying to do autonomous driving, they are struggling with this very much, and we don't know how to solve this yet. This is a very good example, but it's also a very extreme example of something that right now remains unsolved.
Yeah,
that's actually one of the biggest challenges in the automotive industry right now, in this self-driving cars, is that in order to guarantee safety in those very rare circumstances, they would need to do so much testing that it's completely infeasible. And right now, really nobody has any idea how to avoid that.
Yes. Okay.
Good. So in the data mining, there's also a number of kind of related disciplines. So the data mining is not kind of on its own. It builds on a lot of different areas. So one of the important aspects is, of course, the database technology, because data mining is built on large amounts of data and you need to store it somehow. Data mining combines a lot of approaches from machine learning, statistics, and pattern recognition. So all of those domains are very important. There is a lot of algorithmic work. A lot of what you would want to do in data mining has very high computational complexity, so you need to spend quite a bit of time trying to optimize those different things. Visualization is very important, because once you discover some kind of knowledge, it's not really useful unless people can understand the output. So different ways of visualizing things are very important. So in general, the data mining is a very interdisciplinary area. So there is a lot of overlap with other domains. And if you think about what is the kind of core of data mining, all of the data mining is more or less about finding a good model that fits the data. And the model can be very different ways, but still you want to have a good way of fitting the data. And the challenge is that for different tasks, for different kinds of patterns that you want to find, you need different criteria that lets you choose one model over another. And on one hand, all of this is based on ways to compare different pieces of data. So if you would have two different images or two different customers, you want to have different ways of measuring how similar they are to each other, because all of the data mining is about finding out good groups of, let's say, customers who behave in a similar way. If you can find good groupings like this, then you can use it to predict future behaviors and so on. The task is, of course, or the challenge is that those comparisons are often very difficult, because not all the information is equally relevant. And when you talk about, let's say, buying behavior for customers in supermarkets, many of the features of the customers are not really that important, and figuring out which factors are the main driving forces behind the buying behavior, that's the very tricky thing. But if you think of it, there are two main types of models. So one is so-called predictive models, where the goal is to infer unknown values based on known data. So you basically have a partial description of the data, and you want to fill in the gaps in this description based on the training data that you had. And the other type of models are descriptive models, which kind of identify and expose patterns in the data. So in this case, you don't focus on the unknown data, but you rather focus on summarization and comparisons on different ways to describe those data items. So if you think about what has been the most useful or most successful approaches, many of those are based on supervised learning paradigm. And the challenge with supervised learning is that it actually requires usually quite a large training set. So in many cases, it's difficult to get such large sets of data. So there has been a lot of research, for example, on what can you do when you have a data which has some supervised labels, but they are not very trustworthy. Also, if you look at the kind of more typical machine learning research, this usually assumes that your quality criterion is known. So you know exactly what you are trying to optimize. So you could try to have high accuracy or F-score or area under ROC curve, a number of different measures of it. But when you look at it from the data mining perspective, it's often that the actual problem that you are trying to solve doesn't match a particular quality criterion very well. Also, the question is what kind of data should be used for final analysis? Because in many cases, you have some, so you would do this kind of data mining pilot project, and in this pilot, you could have some amount of data, but then it would turn out that when you try to deploy this kind of the solution, it turns out that in this research or pilot project, you had access to more data than what you actually have available in the production systems, and then you cannot really do it. Or it turns out that the way the data has been selected for this pilot project was in some way biased. You have picked the easiest cases, and when you try to do it more broadly, things don't work so well. So there is a number of kind of challenges related to how to actually take the small-scale data mining projects and turn them into bigger scale. So those are things that's important to think about. Will you actually be able to scale up the solutions that you are working on? There's one kind of interesting, I think, direction I wanted to talk about, which is maybe not so much related to industry applications. But if you think about how the concept of science has changed over the years, like what does it actually mean to discover new knowledge? If you just go back to like until, let's say, 17th century, we had what we called empirical science. And back then, the science was about just observing and writing down things. So you would measure things, write it down, and that was getting new knowledge. It's only in the, let's say, between 1600s to 1950s, we started talking about theoretical science. So the theoretical science was based on the theoretical models. So we would build a model of how the world should behave. We said, we have a certain level of understanding of the world around us. And we think that the world behaves this way. And then we will, based on those models, design experiments to check if our models are correct or not. So in a sense, we would use models and experiments to generalize our understanding. It was not only about observations, but it was about finding patterns in those observations and then doing more experiments to see if those patterns will hold in the future. And that's kind of the baseline of what we would think the scientific method is about. We say, this is our hypothesis, this is what we expect will happen, and then we perform the experiment, and we it either conforms to our hypothesis or we need to come up with a different hypothesis. But turns out that you can go farther beyond that, because let's say around 1950s, we started talking about computational science. And basically in every branch of science, we now have the computational version. We have computational biology, we have computational linguistics. Wherever you look, you have the computational version. And that basically means that we have reached a stage at which the models that we are building are too complicated for us to understand and are too complicated for us to design new experiments. We need computers to help us with dealing with this. Generally, that means using different kinds of simulations. And then some people started saying that, let's say, since 1990s, maybe since 2000s, we are starting to actually talk about data science in terms of the amount of data we are getting from the scientific instruments, scientific simulations is so big that it's not only the design of experiments that's beyond the capability of kind of unaided human mind, but it's also the creation of new hypotheses. That's something that we cannot do anymore. That today we need to use something like data mining in order to come up with new possible models for our world. I think that that's kind of an interesting way of thinking about how our way of thinking about the world has evolved. And now maybe to switch a little bit into the pitfalls of doing data mining. So one important thing is what is called Bonferroni's principle. And that guy said that if you look harder than the quantity of data supports, you will find some kind of pattern that fits. And this is one of the main challenges with doing data mining. We are working with models which are so complex and so expressive that you can basically always find a model that fits whatever data you have. And that doesn't necessarily mean that the model is correct, just means that you have tried so many different things. With today's computers, computational power, and the amount of tools that we have, we can do so many different tests that it's possible, almost always possible, to find some kind of model that fits. So one of the challenges is that if you kind of go back to some of the, let's say, older sisters of data mining, for example, in statistics, there are certain quite well understood limits on what kind of knowledge can you extract from a given amount of data. So you would know that if you have 100 data points, you cannot reliably fit anything bigger than, I don't know, maybe a level 3 polynomial or something like this. But we don't have similar rules for data mining. So in general, there is a lot of people who are trying to use very complicated data mining methods with the amount of data which doesn't really support it. And part of the challenge is, of course, that again, we don't really have easy guidelines on how complicated you can do it. But it's at least important to understand that this is a possible problem. And kind of one
but sorry, yes, one question.
Sure.
Do you mean that there are methods, but they are very hard to understand when you say it's hard to formalize? Or
I think this again goes back to the kind of art versus science question.
Yeah.
I think this is something that comes with experience.
Mm-hmm.
I don't know how to teach those kinds of things.
I see.
This is very much an intuition thing. Kind of just to give a little bit of examples of things like this. So there is this thing called Rhine paradox, and Rhine was an American scientist who actually wanted to do parapsychology research using scientific method. So he has this hypothesis that some people had extrasensory perception, and he tried to validate this claim using scientific method. So in one of his experiments, he had a number of subjects who were supposed to guess symbols on 10 hidden cards. Each card was randomly chosen from 5 different possibilities. And his conclusion was that almost 1 person in 1,000 has ESP because they were able to get all 10 right. So he's done this experiment. He identified the people with ESP. And then basically, so he said, okay, quite interesting. Let's double check if it actually works. So Ryan told those guys that they had ESP, and then please come back for another session. We want to double check things. And unfortunately for him, the results from the second test, they didn't really work out. The results were pretty much the expected number of random correct guesses. So what was the conclusion? Can you guess the conclusion that Ryan got? What do you think is the conclusion from this?
I don't know actually.
No idea.
He manipulated his data.
Well, that's not what he concluded. He basically figured out that you actually shouldn't tell people that they have extrasensory perception, because once you tell it to them, then they lose it. And on one level, sure, that's a perfectly valid conclusion from this particular experiment, right? They had extrasensory perception until he told them about it. So that's one kind of example. If you would look for an explanation that explains what has been observed, that's a valid explanation. That would work. But of course, it's not very convincing, right? That's not really what happens. Turns out that the actual design of the first experiment was flawed. It was possible to see enough of the information on those cards that people weren't really guessing at random. They got enough hints to get much better than random results. The second experiment was much more carefully designed. But the point here I wanted to make is that if you just look for an explanation of the data, you could end up with something like this. And for us, this particular conclusion is obviously not acceptable. But if you would try to have an automatic system would not know that this conclusion doesn't make sense. Right? It does explain the data. So basically, for any amount of data, you can always find an explanation which would explain this data, but not in a very, very good way. So that was just one way of intuitively explaining this concept. And then, as we said, the main idea behind data mining is to find interesting patterns. So the challenge is it's very, very difficult to really formalize the concept of interesting patterns. And Stefan will talk a little bit more about it in one of the next lectures. But one of the challenges is that if you look at data mining methods, they will usually generate a lot of patterns, and most of them will not be very interesting. So you need to have some way of filtering based on those interestingness measures. And there are several different ways of looking at it. Of course, for example, easily understood by humans is one interesting criterion. You would want the patterns to be easily to understood. You would want the patterns to be valid on new data with some degree of certainty. You would want the patterns to be useful. You would want them to be either novel, so something you didn't know, or validating a hypothesis that you seek to confirm. So those are all examples of what kind of patterns you would be interested in. But again, all of those are very kind of fuzzy definition. It's difficult to formalize them. There has been a lot of work put into trying to find different ways to formalize those kinds of concepts, but with some kind of limited success. So if you look at it from more scientific perspective, people have divided interestingness measures into two different types, the objective or subjective interestingness measures. So the objective ones are based on statistics and structures of data. And those examples would be things like support, confidence, accuracy, and so on. So those are basically the measures that you can get from the data itself. The problem with those is that they don't necessarily correspond to those kind of criteria that we really would be interested in. And then the subjective measures are based in one way or another on users' belief. So here we could have examples such as unexpectedness, novelty, actionability, all of those things which are much more interesting from, let's say, business perspective or from the perspective of actually getting something out of the data mining approaches. But they are much more difficult to kind of calculate and to put a number on and to actually compare different patterns. So this kind of duality is present in a lot of different areas of data mining, where you have on one hand the nice formal ways of measuring things which are easy or that is possible to calculate, but don't really correspond 100% to the goals of the user, and you have the kind of fuzzy subjective ways of looking at things which really capture users' interest, but where it's really difficult to objectively say if a particular method was successful or not based on those criteria. So a lot of research and kind of practical applications of data mining is trying to be somewhere in the middle, taking a little bit of each to make sure that you are getting both results which can be compared against other methods and results which you know will be useful for the user. Another challenge with data mining is how many different types of data you can be working with. And if you look at it, one very popular way or type of data is data streams and sensor data. So anytime you have anything measured, you would collect this as a time series data. You can have temporal data, sequence data. This can be from sensors, it can be from different kinds of events, but anything that's based on time. You can have structured data. Especially today, there is a lot of work on analyzing social network, analyzing different kind of linked data, graphs, relational databases. So basically data in which you have different entities with different kinds of relations between them. There are different kind of heterogeneous databases. So for example, multimedia and finding patterns in images, videos, that's its own challenge. There is a lot of data in text databases, the biggest one, of course, being the Internet or World Wide Web. And if you try to do data on text or data mining on text, that comes with its own challenges. So a lot of data mining is, at least to some degree, independent of the data type. but a lot of this is also specific. So you would have a number of algorithms that only target text data or only target image data and so on. And it's kind of important to understand those constraints. And on the other side, it's also, as I mentioned, there is a lot of different patterns that you might be interested in discovering. So, for example, one big question is, are you interested in precise or approximate patterns? So in many cases, when you are trying to find something that fits your data, you can find a precise pattern. So you can find a model which fits your data exactly. But also in many cases, if instead of this exact pattern, you would use an approximate pattern, you could have something which is much more compact, much more easy to understand. And then it turns out that in many cases, it will also generalize better. So there is a trade-off here about how precisely you want to fit your data and how much would you expect the results to work in the future. Also, the question is, do you want to find constrained or non-constrained patterns? So the idea being, do you want to specify what kind of patterns you want to find, or do you want the data mining algorithm to work as a kind of black box thing where you don't need to specify anything, that it will give you all the different kinds of patterns. And the challenge here is what is called the no free lunch theorem. I will talk a little bit more about that later, but it's basically that if you know what you are looking for, if you want to, if you are able to add domain knowledge to the data mining process, then you will end up with generally much better results. But it's not very easy to combine data-driven and knowledge-driven approaches. In many cases, there are many approaches which only consider data or which only consider domain knowledge, while combining the two can sometimes be difficult. So there is a lot of quite interesting research on how to push the domain knowledge into the mining process. So all of those things are important, again, when you start thinking about what kind of data mining methods you would want to be using. So if you think of the modeling for data mining, this always has kind of two stages. So you start by using some kind of data, usually historical data, to create a model. And then once you have your model, you want to use it on new data in the future to actually get some kind of benefit from it. Right? So if we look at supervised machine learning, so what we have is we have the historical data of some examples, and we know that each example belongs to a predefined class. So for example, we want to be working with images. We might have some images, and we know that there we have 1,000 images of cats, and we have 1,000 images of dogs, and we want to learn to distinguish cats from dogs. Or it could be in some kind of monitoring scenario. It could be distinguishing between employees of a company and guests to figure out who should get access and who shouldn't, whatever the classes could be. So given this kind of training data, we want to build a model. So it could be classification rules, could be decision trees, SVM, any kind of model to fit this data as well as possible. So to basically learn to what kind of features distinguish between dogs and cats. And then we would want to evaluate the accuracy of this model. So we want to know if our model actually works or not. And we want to try to do it on some kind of independent set so that we don't overfit. So this is about model construction. So once we have done this work, then we know that we have, let's say, neural network, and we know that this neural network has accuracy of maybe 95% in distinguishing between cats and dogs. And then the next step is model exploitation. Once we have this network, we need to figure out how to use this in order to draw conclusions about new examples. So we will be given a new image, and the network will be able to tell us, is it a cat or a dog? And then the question is, what will we do with this information? And then the question is, how do we exploit this model based on things like the accuracy that we have gotten? Of course, if the accuracy is high, we can trust this model more. If the accuracy is low, we cannot trust it so much. So in what way we will be able to use it depends on things like that. It's also important to figure out for how long we expect this model to be valid. So cats and dogs maybe don't change so much, but if we would train our employees versus guests, at some point you would need to retrain, because the list of employees of a company is not constant, that changes from time to time. So it's important to understand that when you create such a model, that model doesn't necessarily need to stay valid forever. It might be that at some point you will need to recreate the model with some new data. And then if we look at what kind of tasks we would want to be able to solve with data mining. So we've talked about the predictive and descriptive tasks. So in predictive tasks, we would mostly talk about things like classification, regression, prediction. So we basically want to, for example, map the data into predefined classes. So we see a new image, we want to know if it's cat or dog. Or in regression case, we would want to approximate the data with some function. So, for example, we would train the stock market model, and then we would want to know what will be the price of a particular stock price at a particular day, and so on. So most often you would do this kind of predictive reasoning using supervised learning. So you'd have some kind of training data with examples of what you want to achieve, and this data would usually come from historical information, and then you would want to use this to predict the future. And the other way of doing things is the descriptive analysis, and in this case it's usually unsupervised learning. So here you wouldn't necessarily know you wouldn't have the training data with some supervised labels. So here you would have tasks such as clustering. So this would be about finding groups of similar items. You could have, let's say, your customers from a supermarket, and you would want to say, find me 5 groups of 5 different types of customers. That would be the task. Or it could be association rules, where you would find relationships between items. So what types of goods are usually bought together? You could have characterization task. So you would want to derive representative information. So you would want to say, what are the most critical features for heavy-duty truck versus a bus, or any other differentiating information. And then if you look at some examples of what you could do, I think that this will be quite simple. So for classification and prediction, the goal is to focus on discriminating features. So you want to find what's different or what's separating the different classes. For example, if you have your customers and you want to segment them into some kind of risk segments, you want to know what are the most critical differences between people who will pay off their loan and people who will not pay it off. If you look at something like multidimensional concept description, you want to provide characterization of groups of data points. So you want to contrast different data characteristics. So let's say you have different regions in a country, and you want to say what are the main differences between dry and wet regions of the country. Well, obviously the amount of rain would be one, but you are interested in what else makes a difference. You would want to find things like vegetation and different kinds of different ways in which you could describe the similarities and differences between them. You could look at co-occurrences. So the example of young men buying diapers and beer. And here it's especially important to understand that the correlation does not mean causation necessarily. Right? So just because things are correlated doesn't mean that one of them is causing the other. More examples would be things like cluster analysis. So you want to group data into some kind of classes, basically maximizing intra-class similarity, minimizing inter-class similarity. So you want to say that we have this group of, let's say, customers, and they are all very similar to each other, but quite different from all the other customers. You want to do outlier analysis. So finding objects which do not comply with the typical behavior. So you would say that, well, most customers spend, I don't know, between 50 and 1,000 crowns when they visit supermarket, probably more than 1,000. And if somebody goes to a supermarket and buys something for 1 crown, that's an outlier. That's a strange thing. And then, of course, the question is this some kind of noise? Is it something, maybe the sensor was broken or whatever? Or is it actually an interesting exception that's worth some kind of analysis? And that can be useful, for example, in things like fraud detection and so on. And then you want to also be doing different kinds of trend and evolution analysis. So, for example, measure trend of different things, deviation from this trend. You want to measure periodicity. You want to find similarities between things. You can do sequential pattern mining, so different kinds of basket analysis. If I buy something today, what will I buy next week, and what will I buy next month, and so on. All of those kinds of approaches are examples of data mining tasks. And I mean, I'm sure you can see now that one of the big challenges with data mining is that there is so many different tasks that in many cases it's hard to find similarities between those kinds of methods. So data mining as a field is a very broad one with a lot of different algorithms which essentially solve different problems, and the only thing they have in common is this idea of discovering new knowledge. But if you look at it somewhere kind of more in a more abstract way, you basically, most of data mining at some level boils down to either supervised or unsupervised machine learning. So again, just to kind of summarize, in case of supervised learning, if you think of classification, you have training data with target labels. You have new data which is classified based on the patterns you have found in the training set. And because you have those target labels, you want to focus only on the relevant information. So you only want to focus on the information that distinguishes between the two classes that you are looking for. And you can evaluate results in an objective way using something like accuracy. In case of unsupervised learning, let's say clustering, because you don't have any labels in the data, the target task, what you are actually trying to do, is a little bit unspecified. It's somewhat subjective what exactly you want to do. You want to discover some kind of structure that exists in this data, but it's very open-ended problem. So if you want to find clusters, you will take advantage of different kind of similarity measures defined between objects. But there might be different types of clusters or different clusters depending on what you are interested in. And then if you compare classification and regression, so classification is when you have small number of target classes. So we want to distinguish between, let's say, cats and dogs. And regression is when you are trying to predict future values of a function, usually continuous function. So in a sense, both of those focus on a relation between one or more independent variables and some kind of response variable. But in classification, when you have categorical labels, what you are learning is the conditional probability. What's the probability of class X, given the description Y? So basically, you want to focus on the differences between classes. While in regression, when you try to predict values of continuous function, you are creating the more generative model, which focuses on the unknown values. So you basically learn the joint probability was the probability of X and Y. So we will talk more about that in future lectures. But the most common, by far the most common way of doing machine learning is the supervised machine learning. So here the goal is to find patterns that explain or are associated with certain target labels. And one of the most common examples, the kind of toy examples of this is the iris dataset. So you have different types of iris flowers, and they are described by different features. So for example, petal width and petal length. And you can see that different species of this flower are different based on those parameters, but there is some kind of overlap between the red and blue ones, which makes it somewhat, at least, a non-trivial task. So in supervised machine learning, you need a representative training set, and then you want to make predictions based on that. So you can use exactly the same techniques for the iris dataset. You can use it for training, for example, spam filter. So you would train it based on a list of important emails and everything else, and then the machine would be able to predict those things. But the challenge here, of course, is to make sure that the training set you have is really representative. Because if your training set is not really representative, if there is something special about it, and most of the data in the future will not look like it, your model will not work, as you can see. And if you try to predict the trend of number of husbands based on the wedding day, you are likely to make quite a bit of mistake. And in unsupervised learning, on the other hand, it focuses on finding patterns in data. So the most common way of doing that is clustering. So in clustering, you would find different similar patterns in the data. And as I mentioned, the challenge with clustering is that this is so subjective, because you can try to cluster based on different criteria. If you look at, let's say, those characters, you can cluster them perfectly, reasonably, based on different criteria. The clustering of females versus males makes sense, but the clustering of Simpson's family versus school employees, that also makes perfect sense. Another example of unsupervised machine learning would be anomaly detection, when you want to try to find things which don't match the general patterns, and so on. And then when we talk about machine learning, we mostly talk about statistical machine learning. So we are looking for statistically significant patterns in the data. And we want to do it using algorithms and processing power of computers, because obviously there is a lot of different potential patterns you could look for. If you really want to make it, it will take quite a few computations. So what you basically do is you try to base those models on mathematical properties of the data, and usually some kind of noise models. So you assume that the data that you have, it corresponds to certain properties of the real world, but it's usually contaminated by some kind of noise. So you are trying to account for the noise and discover the real properties. So if you think of a learning problem as kind of what really you want to do, the goal is to improve a particular task with experience. And that means that in order to formalize it, you need to figure out what kind of task you are trying to solve, what kind of performance measure you are using, and what kind of experience information you have access to. So the other important thing is that the goal is generalization, so the good performance on unseen data. So the goal is, of course, not to be accurate on the training set, but to discover patterns from the training set that you expect to be applicable in the future as well. So if you look at the inductive learning example, this can be about, you have some amount of data points, so it will be the dots here, and you want to find some kind of hypothesis or a function that agrees with those examples. And if a hypothesis perfectly agrees with this, if it's then we call it consistent. So if the hypothesis is has exactly the same value as the target function f, then we would call it consistent. So here is one easy example. You have 7 different points, but they all lie on a line. So you would say that here the hypothesis would be a single line. But of course, that's not the only possible hypothesis. You could also imagine that the same 7 points could come from a very different function, like the one here. There is no obvious reason why example A would be better than B. Both of those fit the data perfectly well. Also, you could imagine, like in example C, if you have data which is not on a line, now you can have 2 different possibilities. You could have the red line, which fits the data perfectly, but it's quite complex. Or you could say that you like the green line better, even though it doesn't fit the data so well, but it's very simple. It's just a single line. Or you could also say that this data actually comes from some kind of a sinusoid function. So all of those examples are examples of different hypotheses that would explain to better or worse degree this particular data. And the underlying concept under all of the machine learning is that in order to achieve good generalization, you want to find the simplest consistent hypothesis, or the simplest almost consistent hypothesis. So if we look at our examples here, the first one would be consistent linear fit. So that looks great. Example B would be consistent 7th order polynomial, but we would assume that linear fit is better because it's a simpler hypothesis. We prefer polynomial of degree 1 over polynomial of degree 7. In example C, now we actually have a choice to make, because either we can pick an inconsistent linear fit, so a line which doesn't fit the data perfectly, but it fits okay, or we could pick a consistent 6th order polynomial. So data which, or model which fits the data, but it's quite complex. So it's hard to say, without knowing anything about the type of the problem we are trying to solve, which of those could potentially be better. And then in example D, we actually have a consistent sinusoidal fit. And then the question is sinusoid considered a simple model or a complicated model? If we expect from the domain knowledge that sinusoid is something that makes sense, like if we are talking about, I don't know, let's say something in electrical grid, then sinusoid might be a perfectly good model, and it makes sense. So that's the basic idea behind machine learning, that you want to find different kind of hypothesis that matches your data to some degree. I will have to speed up through a couple of slides here where maybe we don't need to go into all of the details. So here the idea was that the data was represented as kind of points in space, but often the data is also represented as just kind of a table. So we could have here 6 different attributes, and we are trying to figure out if the person will enjoy sport or not based on the values of those attributes. And then in here again, the hypothesis was represented as a function. This was just a continuous function of one variable. Here, we would want to represent our hypothesis as some kind of a rule. So we could say that we put constraints on our attributes. So we can have either a specific value for the attribute, or we could have a don't care. So one possible hypothesis would be like this. If it's sunny and wind is strong and forecast is the same, then we will either enjoy sport or not. We don't care about the values of the other attributes. So this is one way of representing a hypothesis. If we have a hypothesis like that, we can classify any example. It will tell us if we will enjoy sports or not. And the interesting thing is that you can have ordering of hypotheses from general to specific that corresponds to different sets of instances. So every hypothesis, and here we are just talking about a binary task, so the answer is always either yes or no. So any hypothesis corresponds to a set of instances or examples for which this hypothesis returns true or false. And that means that you get a lattice of hypotheses, a grid of hypotheses, where you can say that one hypothesis is more general or more specific than the other because it will cover the same examples. But you can also end up with hypotheses which are not comparable. So here, for example, hypothesis 3 is more general than hypothesis 2, but hypothesis 3 and 1 are incomparable. And then one idea of doing machine learning would be to just try to find the most specific hypothesis which is consistent with all of our examples. But the challenge with doing something like this is that if we only limit ourselves to the most specific hypothesis, we don't really know how well the concept has been learned. Do we need more training examples? Maybe we haven't been able to narrow down well enough. We also cannot tell if the training data is inconsistent because we are just ignoring all the negative examples. And then we decided to pick a maximally specific hypothesis, but there is no immediate reason to believe that this is better than any other hypothesis. Maybe we can find some other hypothesis. So what we could also do is we could try to find what is called version spaces. So all the hypotheses which are consistent with our training data. So again, we've talked consistent hypothesis is one which agrees with target on all the examples. And then a version space would be a set of all the hypotheses which are consistent with our training data. And if we think about this or such a set of hypotheses, you actually don't need to list all of them because it's enough to think about what's the most specific and the most general hypothesis in this set. And you can represent the whole set using just those two. And I will skip this thing. So basically, the underlying idea behind machine learning is this concept of IID data, which stands for independent and identically distributed. So what we basically assume is that there exists a single underlying true distribution of the data that we want to model. And then all of our training examples are drawn independently from it, which means that our data samples cannot be related to each other. And also that all the future data will come from exactly the same distribution, which means that our training and testing set will be done in similar setting. So there is an issue with this kind of assumption that, for example, in adversarial settings, this leads to certain issues. And if we think of areas such as security or forensics or malware, that can be a challenge, because if we assume that the testing and training data comes from the same distribution, then we can learn once and we can base our predictions on what we have seen in the training data set. But if we assume that we have trained our system and then there is some kind of adversarial or enemy who can adapt their, let's call it, attacks to what we have learned, so they can modify their behavior based on our trained model, that requires quite a different approach, and most of the typical machine learning will not really work. So you may have heard about this concept of deep learning, and one of the challenges with deep learning is that it's actually it's quite easy to fool this into making mistakes. So one of the success stories behind deep learning was, of course, image recognition. So here you can see the example of, on the left-hand side, there's an image of panda, and there have been several different deep learning algorithms that are able to recognize images like this with reasonably high confidence. So this one here would have 57.7% confidence that this image is actually a panda. And that's great. But the challenge is, if you add to this panda a little bit of noise, so just the middle example doesn't seem to contain anything of interest. And in fact, if you combine the left image with this noise, you end up with the right-hand image, which to a human eye looks exactly the same. We cannot really distinguish between the two images. But this image has been modified to a such degree that the same deep network now will answer that this is not a panda, it's a gibbon with 99% confidence. So this is one example of what can happen if you violate this IID assumption, because now this right-hand image, it actually is different from the network's perspective, from the data it has trained on, and that's one of the challenges.
So to do this kind of to fool the network like this, do you need to know how the network is built, or can you do it in another way, or do you need knowledge about the network?
You need knowledge about the network. So this one actually requires you to be able to, but not only the network structure, but the exact information about the weights and so on. So you need to be able to measure gradients in different places. So another thing I wanted to mention is this no free lunch theorem. So the idea here is basically that it's already Hume in 1800s who said that in general, even after you have observed certain pattern, you don't necessarily have any reason to draw inference about the future. And also that this kind of thing has been formalized in several papers about if we assume that all the different target functions are equally likely, then all the different learning algorithms will on average behave the same way. So I will not go into too much details here, but you can also look at it from the more mathematical perspective when you look at the conditional probabilities. But the basic idea is that just because we have observed certain amount of data, without any a priori assumptions about what kind of functions we are trying to learn, we cannot make any predictions about the future. So the idea why all the machine learning algorithms work is because the interesting patterns we are trying to predict, interesting functions, interesting behaviors in the world, they all share certain common characteristics. So all of the machine learning algorithms introduce what is called a bias. So they make certain assumptions beyond just the data that they are observing, and the actual quality of the solution you are getting depends on how well does the internal assumptions embedded into the machine learning algorithm actually fit a particular task in which you are using it. So this is an important thing to understand, that most of the success of machine learning is about finding the right algorithm for the particular task. And again, the challenge here is that we don't really have good formal ways of doing it. That again kind of boils down to the more of an intuition of whoever is doing the data mining. And that also boils down to kind of comes back to what would be the best machine learning algorithm and so on, and why there are so many different machine learning algorithms and nobody can agree on which one is the best. And there is some interesting thing here. For example, in the International Conference on Data Mining in 2006, they've done a survey of what are the top 10 algorithms, and here is the list of this. And surprisingly enough, they have never done this survey again after that, even though the paper that reports those results has 3,700 citations. So obviously, that's a very important thing to have. People like to have lists like this, but the kind of controversy around this, it was so controversial, that this idea, that they haven't done it on any of the future conferences. I mean, to me, it sounds quite interesting, but it's just something to think about. And I think we are running out of time, so I will not. I have a couple of kind of finishing.
In what way was it controversial?
Well, a number of people didn't like the final ranking. You know, all of those algorithms, and probably some of those which are missing here, have very vocal proponents. So, to be honest,
politics and gaming.
Yeah, probably. I mean, I'm very surprised that this has not been done after that. I would really expect this to be done more often. And the only reason I can imagine is because people were upset about the results here. I think that is quite interesting. But,
I mean, it's also would it be some depending on? I guess these different algorithms are available for download or similar. That you have a list of how many people have downloaded each and every version.
So those are just the votes from the conference, but yes, all of those algorithms are available. most of them are available in a lot of different libraries or tools and so on. So those are all very popular algorithms.
Yeah.
Okay, so I think I will just finish here. So that was the introductory lecture, and then I guess in 2 weeks we will talk more about specifically the decision tree learning algorithms. Any questions, final comments?
Yeah.
How many slides was it?
A lot. I think it was 60.
It was very interesting. I enjoyed it.
Great.
Yeah.
I did a master thesis back in 2002 where we predicted exhaust gas temperatures based on 6 measurements from a combustion engine.
Okay,
And
sounds interesting.
yeah, back then it was named artificial neural networks, but I guess I was doing data mining actually, predictive data mining.
Yes, exactly.
Yeah.
I agree with Herman. For me, this was very helpful, and if it's the other lectures are like this, I will learn a lot. So, yeah.
Hey.
Thank you.
Great. Thank you very much.
Are there any homework to do till next time, or will it be a lecture? And because it was stated in the curriculum that there will be some work to do in between.
Yes, there will be work in between, but I don't think we have planned anything after this first introductory lecture, because that was more of a kind of overview, and I think after the next lecture there will be more. Then there will be homework. Yes.
Yeah. So there will be some assignments, but that means you will get all this through the interactive tool. So the assignments and so on will be presented to you sort of continuously as we go along and so on. So you will not get like everything at once.
That's perfect. That's perfect. And another question, because you described these things very well, I think, but are there any recommended book or something if I want to more dig into the details of some of the topics here, or some acronyms or things like that?
In the course plan, we have defined the course literature. So there's a data mining handbook.
Okay.
So we could send you the reference to that.
Please do that so that I can order the book.
I can actually put it in the slides as well, because I don't have it here now, but I can add a slide with the book, so that.
Nice.
But we will also send it to you.
Thanks a lot for today.
Great. Thank you very much.
And see you in 2 weeks, I guess.
So, talk to you later. Bye bye.
Yes, bye. Thank you very much. Have a nice evening.
Have a nice evening. Bye.
Bye.